Hi everyone, thanks for watching another TheCurioCat video. This will be the first video of the TheCurioCat Open Science Project, where we make complicated science accessible to everyone. Our first project is called Senior Thesis, Modeling Electromagnetic Fields. The complexity and thoroughness of this project will be approximately at the college senior level. However, I will explain this project in a very simple step-by-step way so that even a high school student can understand. Okay, now for the project prompt. Assume that you are given a length of wire. This wire has a circular cross-section. This will be used to conduct an AC electric current of frequency 60 Hz. Please complete the following 3 goals. Goal 1 is to compute the electric and magnetic fields inside the wire. Goal 2 is to use those electric and magnetic fields to calculate the impedance of the wire. And in this project, I will explain what is impedance and what is the practical application of knowing the impedance. Goal 3 is to plot the current density distribution in the cross-section of the wire, and we can do this plot using Python. The intended learning outcome is for students to have a better understanding of electromagnetic fields, and also for students to obtain some usable research skills. The intended audience is advanced high school kids and up, meaning that if you have at least some knowledge of calculus, then this video series will be accessible to you. For some inspiration, here are 2 current density distribution polar plots for the cross-section of 2 conductors. On the left, you have an aluminum conductor, and on the right, you have an aluminum-clad steel reinforced conductor, also known as an ACSR conductor. Both conductors have a diameter of 0.6129 inches and carry a current of 1 ampere at a frequency of 60 Hz. In this project, I will teach you step by step, very slowly and very carefully, how to get these polar plots, starting with very basic fundamental equations. The first equation that we need is called Ohm's Law. To understand what this equation means, we will look at a wire. Here I have drawn a length of wire. The length of the wire is L, and the cross-sectional area of the wire is A. Between the top end and bottom end of the wire, I will now apply a voltage. On the top of the wire, I have drawn a bunch of plus signs to show that it is connected to the positive terminal of the battery, and at the bottom end of the wire, I have drawn a bunch of negative signs to show that it is connected to the negative end of the battery. From physics, we know that electric field lines extend from positive charges to negative charges, so we can draw those field lines now. Due to the applied voltage, we also know that a current will flow down the wire in the same direction as the electric field. There is another form of Ohm's law that can relate the voltage and the current. That law is V equals IR, where R is the resistance of the wire. If you're not very familiar with voltage, current, and resistance, please watch the TheCurioCat circuit analysis videos. There's a rule that the voltage is equal to the electric field multiplied by the distance between the positive charges and the negative charges. There is another rule that states that the resistance of a wire is equal to its resistivity multiplied by its length and divided by its cross-sectional area. We can now eliminate the length from both sides of the equation. Now looking at the right side of the equation, we see that we have a current I divided over a cross-sectional area A. We can replace I over A with a letter J standing for current density. We can now rearrange this formula to solve for J. The fraction 1 over rho is equals to conductivity. So we can rewrite the equation as follows. And now we have our current version of Ohm's law. The takeaway is that the current density J and the electric field E point in the same direction, and they are related according to Ohm's law. The next equations that we need are called the time harmonic forms of Maxwell's equations. So here are some things to understand. The time harmonic form is also known as the phasor form. The time harmonic form is a simplification we can make if we assume that the fields are time harmonic or sinusoidal. And you can identify the time harmonic form due to the imaginary number J in equation 3. Finally, there are actually 4 Maxwell's equations, but we only need 3 of them. Now I will explain to you what is equation 2, which is called Amperes Law. For equation 2, you can read it like this. The curl of the magnetic field H is equal to the current density J. This sounds really complicated, but it's actually very easy. I will explain using a wire. So on the screen, I have drawn a wire with a current density J. From physics, we know that an electric current going down a wire will create a magnetic field around the wire. And the direction of the magnetic field depends on a rule known as the right-hand rule. To make this example a little bit more clear, I will redraw this picture so that the wire is coming out of the screen. According to the right-hand rule, if the current is coming out of the screen towards you, the magnetic field should go in a counterclockwise direction. However, our electric current is a sine wave, and sine waves are alternating currents. This means that the direction of the current changes direction back and forth, back and forth. So here I've drawn the case where the current density is going down the wire into the screen away from you. In this case, you see that the direction of the magnetic field is clockwise. Here is a GIF that shows how the magnetic field changes direction due to the alternating current. So the key takeaway is that a current density J creates a curling magnetic field H. So the curl actually means that the field is actually curling in a circular direction. Now I will explain equation 3, which is called Faraday's Law of Induction. Currently, equation 3 is written in the time harmonic or phasor form, and this actually makes the equation look a little bit more complicated. So I will rewrite the equation in the differential or point form. Here, the symbol mu stands for magnetic permeability. Now there's a rule that says that the magnetic flux density B is equals to mu H. This means that we can replace mu H with B. Now we have the point form of Faraday's law, and this will be much easier to understand. Here I have redrawn the diagrams showing the magnetic field around our wire. So remember that the magnetic field constantly changes direction from counterclockwise to clockwise and back to counterclockwise due to the alternating current. Now imagine that we place a metal loop, which I've drawn in green, into the magnetic field in such a way that the magnetic field lines goes through the center of the loop. You need to visualize in 3D. To help you guys out, I've drawn a very rough 3D picture. Now you see the picture up here, the magnetic field line is going into the center of this green loop. And for the magnetic field lines down here, you see that the magnetic field line is coming out of the center of this green loop. Now, what effect does the magnetic field lines going through the center of the green loop have on this green loop, this green wire? The answer is that it will actually create an electric field inside this wire. So you see up here, this magnetic field lines going into the center of the green loop creates this electric field going around this wire. And the same situation down here, when the magnetic field line comes out of the center of this green loop, it also creates an electric field around the wire, but in the opposite direction as above. Now look back at the equation. You notice that it says d dt, which indicates time varying. What this means is that this electric field will only be created if the magnetic field line is varying with time. And we see here that it's varying because you see here is magnetic field line is going in, then it's coming out, and then it's going in, and then it's coming out. It is this time varying nature of the magnetic field that creates the electric field. As we learned previously, electric fields causes current to flow. So Faraday was able to find that these electric fields existed because he was able to detect a flow of current in this green loop of wire. So the key takeaway is that a changing magnetic field induces a curling electric field. And you can see that the electric field is indeed curling because you see it's going around in a circular motion. At this point, you might ask, You showed us an example of Faraday's law of induction for an H field outside a wire. But what does this have to do with our project? Aren't we looking at fields inside the wire? Well, the answer is that there are H fields inside the wire too. And here's an example showing the magnetic field inside of a wire. Now, Faraday's law is actually a little bit more complicated because Faraday's law shows that a changing magnetic field creates a changing electric field, which in turn creates a changing magnetic field. But we don't need to know all of these details in order to do this project. Now finally, we have reached the fourth equation, which is Gauss's law for magnetism. The way you say this equation is the divergence of the magnetic flux density B is equals to 0. To understand this law, I have drawn a magnet showing a bunch of magnetic field lines. So each one of these lines is a magnetic field line H. According to Gauss's law, if you were to draw some kind of enclosed surface that is inside of these magnetic fields, the amount of magnetic field lines going into and out of the surface should be 0. For example, look at this blue oval that I've drawn. So this oval is actually supposed to represent a three-dimensional shape. So imagine that it is a football, that you are only seeing a cross-section of the football. How many magnetic field lines is going into the football and how many magnetic field lines are coming out of the football? For the lines that are going into the football, I count 4 of them, and they are denoted by the 4 purple arrows. For the amount of magnetic field lines going out of the football, I count 4 of them, and they are denoted by the baby blue arrows. Now I can give you a definition for divergence. Divergence is a measure of the tendency of field lines to go into or out of any particular point in space. If you have more blue arrows leaving the point in space than there are purple arrows going into the point in space, then you would say that the divergence is positive. If you have more arrows going in than coming out, then the divergence is negative. In our case, we have 4 arrows going in and 4 arrows going out. So the net is 0, so the divergence is 0. To make sure that Gauss's law holds anywhere around this magnet, I have drawn an oval in a different location. So for this blue oval here, how many magnetic field lines do you see going in and how many magnetic field lines do you see going out? Take a few seconds to look at it. I see 8 magnetic field lines going into the oval, which I've denoted as purple arrows. And I see 8 magnetic field lines leaving the oval, which I've denoted as baby blue arrows. So again, you see that the net divergence is 0. Here, I would like to illustrate another concept, which is that the electric field and the magnetic field are considered to be vector fields. And you can see that illustrated up here in our example, because you see the magnetic field lines are all shown as a bunch of little arrows. So all of these arrows have magnitude and direction, and therefore they constitute vectors. So because there's a bunch of vectors, this is considered a vector field. So here is a summary of the 4 equations that we have developed so far. H stands for magnetic field strength in amperes per meter. J is the current density in amperes per meter squared. E is the electric field in volts per meter. B is the magnetic flux density in newtons per amp meter. Omega is the angular frequency given by 2 pi f, where f is frequency in hertz. Mu is magnetic permeability in henries per meter. Sigma is conductivity in meters per ohm meter squared, and J is just the imaginary number. Okay guys, so we've covered a lot of material today, so we'll stop here. All of you who reached the end, I really appreciate you guys sticking around and watching to the end of the video. I will continue to post videos until we reach the end of this project. We will drop our engineering videos twice a week, so the next one will come out soon, so watch out for it. If this video is of value to you and you'd like to watch more of these videos, please like, comment, and subscribe. And let me know in the comment section if I'm going too fast or you need more details, or if there are certain projects you want to see me do.